Cosmic Microwave Background, Echoes from the Big Bang. Title: Cosmic Microwave Background, Echoes from the Big Bang. Introduction. Cosmic Microwave Background, CMB, radiation is one of the most significant discoveries in modern astrophysics. It is the faint but uniform radiation that permeates the entire observable universe. The CMB provides invaluable clues about the nature of our universe and its origins, as it represents the remnants of the Big Bang, the event that sparked the birth of our cosmos. This article explores the concept of the CMB, its discovery, and its implications for our understanding of the universe. What is the cosmic microwave background? The cosmic microwave background refers to the radiation left over from the initial stages of our universe's evolution. It is characterized by microwaves, which have wavelengths larger than visible light but shorter than radio waves. This radiation fills every corner of space, carrying valuable information about the early universe. Discovery of the CMB. The quest for understanding the origin and evolution of the universe led to the discovery of the CMB. In the 1960s, Arno Penzias and Robert Wilson accidentally stumbled upon this radiation while conducting experiments with a large radio antenna. They noticed a persistent noise emanating from the sky, which they initially attributed to instrument malfunctions. However, after eliminating all sources of noise, they realized that what they had discovered was the cosmic microwave background radiation. Implications and contributions. The discovery of the CMB had profound implications for cosmology and our understanding of the universe. It provided strong evidence in support of the Big Bang theory, which postulates that the universe originated from an extremely hot, dense, and compact state about 13,8 billion years ago. The CMB serves as an echo of this primordial event, allowing us to probe the universe's infancy. By studying the CMB, scientists have gained important insights into the composition, age, and expansion of the universe. It has allowed them to determine the universe's average temperature and the rate at which it has been expanding over time. Additionally, the CMB has helped establish the existence of dark matter and dark energy, two mysterious components that dominate the composition of the universe. Origins of the cosmic microwave background. The universe's origins are rooted in the Big Bang, an explosion that marked the beginning of everything we know today. In the early stages, the universe was incredibly hot and dense, with temperatures surpassing what we can comprehend. As the universe expanded and cooled, the thermal radiation present at that time began to stretch out, eventually reaching the microwave spectrum. This transformed the early intense heat into a milder microwave radiation that now pervades the cosmos as the CMB. The CMB is a time capsule. Just as archaeologists study ancient artifacts to learn about past civilizations, astronomers use the CMB as a time capsule to delve into the universe's early history. The CMB radiation has stayed unchanged since its release nearly 380,000 years after the Big Bang. Consequently, by analyzing the patterns and fluctuations in the CMB, scientists can glean valuable clues about the composition, structure, and evolution of the early universe. Anisotropies in the CMB. While the CMB appears to be remarkably uniform on a large scale, it exhibits tiny fluctuations or irregularities. These fluctuations, known as anisotropies, reveal the distribution of matter and energy during the early stages of the universe. By studying the anisotropies in the CMB, scientists can gain insights into the formation of galaxies, galaxy clusters, and other large-scale structures in the universe. Cosmic inflation. The existence of anisotropies in the CMB also supports the theory of cosmic inflation. Cosmic inflation suggests that the universe underwent a rapid expansion during the first fraction of a second after the Big Bang. This sudden expansion smoothed out the initial irregularities, resulting in the uniformity observed in the CMB. The patterns seen in the CMB anisotropies align with the predictions of cosmic inflation, further strengthening the model. Future exploration. Scientists continue to study the CMB to unlock more secrets about the universe's history and development. Projects like the European Space Agency's Planck satellite and ongoing ground-based experiments aim to enhance our understanding of the CMB's properties further. By improving the precision of measurements and mapping, these initiatives will provide increased resolution into the earliest moments of our universe. The cosmic microwave background, CMB, radiation is a crucial aspect of modern astrophysics and has significantly contributed to our understanding of the universe. This article will explore the concept of the CMB, its discovery, and its implications for our comprehension of the cosmos. The CMB refers to the radiation that remains from the early stages of the universe's development. It consists of microwaves with wavelengths larger than visible light but smaller than radio waves. This radiation is present everywhere in space and contains valuable information about the early universe. The discovery of the CMB was a result of efforts to comprehend the origin and evolution of the universe. In the 1960s, Arno Penzias and Robert Wilson accidentally stumbled upon this radiation while conducting experiments with a large radio antenna. Initially, they believed the persistent noise they detected was due to instrument malfunctions. However, after thorough investigation and the elimination of all potential sources of noise, they realized that what they had discovered was the CMB radiation. The implications of this discovery were profound for cosmology and our understanding of the universe. The CMB acts as an echo of this primordial event, enabling us to explore the universe's early stages. By analyzing the CMB, scientists have obtained essential insights into the composition, age, and expansion of the universe. It has allowed them to determine the universe's average temperature and its rate of expansion over time. Additionally, the CMB has played a crucial role in establishing the existence of dark matter and dark energy, two enigmatic components that dominate the universe's composition. The origins of the CMB lie in the Big Bang, an explosion that marked the birth of everything we know today.